All right, we're going to do some mechanics today. So this is my first mechanics practice exam. There might be a second one, who knows. The goal with this exam is, if nothing else, just to get familiar with the format. I thought this was of moderate difficulty, maybe a bit above average, but I am hoping that it is more respectful of your time and more manageable than the E&M one. So 40 multiple choice. I really hope to get out of here in under 80 minutes. I did not do that for the E&M one, so that was definitely not enough time for that. But I tried to balance the hard questions with easy ones and tried not to make overly complex derivations. But if not, it's still going to be a good content review. And of course, I post the test folder in the description so you can look at it ahead of time. And I'll also post projections for what I think cutoffs would be for this. All right, question one. Just so you know, we always try to lead with an easy question and end with an easy question. So we have a car that's traveling at constant speed around a circular track. We look at it from the top. What's true about velocity and acceleration during this motion? So we're looking at, is the velocity changing and is the acceleration zero or not? Well, remember that velocity is a vector, which means velocity has direction. So if I'm going at the bottom of the track, I would be moving to the right. Then if I'm at sort of our 3 o'clock position, I'd be moving up and then left and then down. So notice that yes, my speed is the same, which is the length of those blue arrows, but the direction is not, so velocity is changing. And remember, acceleration is defined as delta v over delta t. So I am accelerating. And right, you know this about circular motion. If you're traveling in a circle, you actually do get a constant centripetal acceleration towards that center of the circle. So actually, we do have a changing velocity because we have a non-zero acceleration. So we have a non-constant velocity and a non-zero acceleration. I'd call that pretty easy. That's just kind of a fact about circular motion. A 6 kilogram object is located at x equals 0 and has an initial velocity of 4 meters per second. The object is then subject to a force in that direction. We have a function, and we're given the force as a function of position. We want the kinetic energy of the object upon reaching x equals 2. So kinetic energy and forces. Well, this is going to be work energy theorem, right? Because we know that work causes a change in energy. And in this case, it'll be a change in kinetic energy. So my work done, work is force times distance, but since we have a variable force, we have to integrate our force function, and we're moving from 0 to 2 meters, and our force function is 3x squared. So this antiderivative is just going to be 3x cubed over 3, so we just get x cubed, evaluated from 0 to 8, or sorry, 0 to 2, which is equal to 8. So what this means is that the kinetic energy has increased by 8 joules, or 8 joules of kinetic energy have been added to the object. So we can just say that delta K is equal to positive 8, which means the final kinetic energy minus the initial kinetic energy is equal to 8. So our final kinetic energy is just equal to 8 plus the initial kinetic energy, 1/2 mv squared, and we were given those things. We were given the mass was 6, and the initial velocity was 4 meters per second. And then if we just do that, let's see, half of 6 is 3. 4 times 4 is 16, so this gives us 48. And 48 plus 8 is going to be 56 joules. And that is definitely an answer choice. That is C. So this is multi-step. You didn't just integrate the force, you had to connect it to delta K, so I call that a medium. 2 out of 3. A block of mass M is resting on an incline of angle theta. It's attached by a string to a pulley as shown. What other mass, lowercase m, must be suspended vertically to keep the entire system at rest? Well, entire system at rest, that's constant velocity of 0. So that means we have no net force. Okay, so if we have no net force, that must mean that all the forces balance. So whenever we have a system of objects, we draw what I like to call the big box, where you put all of your system inside a box, because you know that only external forces can contribute to the net force on the system. So what are the forces on this system? Well, normal force isn't going to accelerate this, and there's no friction in this problem. We should actually say this as a resting on a frictionless incline. But if we look at our forces here, the M is getting pulled down on the incline, not by all of its weight, but only the part of its weight directed parallel to the incline. That's mg sine theta. Whereas the hanging mass, all of it is contributing to trying to accelerate the system. Its full mg is pulling. So we can see that our net force is the difference between our counterclockwise acceleration caused by the angled mass, and then we have our clockwise acceleration caused by the hanging mass. So we can just equate those two forces. So we just know that our mg sine theta must exactly balance the little mg. So we want what is the little mass m, so the g goes away, so this should get little m is equal to big M times sine of theta. And that gives us answer choice B. So there was some component things going on, and it was a system, so I bumped it up to level 2. But this is borderline level 1. It's just a standard equilibrium. And it also makes sense that you don't, sine theta is always less than 1, so it makes sense that you don't need as big of a hanging mass to suspend the ramp mass at rest, because you get more bang for your buck for the hanging mass, because all of the mg goes to the string. All right, a block of mass m is attached to a spring with force constant k, frictionless surface. Consider the two scenarios. We compress the spring a distance delta x, or we compress the spring a distance to delta x. And we want to compare the acceleration and the oscillation period when we stretch it double. So what we know for sure is that this is a spring with force constant k. So we know that force is equal to k delta x. So if I double the extension, I must double the force. So this means F doubles, or the maximum force F doubles. And because also we know Newton's second law says that acceleration is equal to F over m, meaning they're proportional, this means that A also doubles at all points. So of course the maximum acceleration will also double. And now what about the period? So you could approach this two ways. So first, if we look at the period of a mass spring oscillator, we have the period of a mass spring system is 2 pi square root m over k. I'm not changing m, I'm not changing k, so the period must stay the same. So you could reason it's c because of that idea, or this is simple harmonic motion, and it's a fact of simple harmonic motion that period is independent of amplitude. That's actually one of the defining features of this. Period is independent of amplitude. So I'd call this level 2 once again, because you had two connections to make. So Hooke's law can get you the double acceleration, but it's a common misconception that a larger stretch does something to the period. It doesn't. It affects the energy and the speed, but it doesn't affect the period. All right. Two objects, x and y, are moving along the positive x-axis. They're starting from rest, but we're given different motion graphs for each object. We're given the velocity of x, but the acceleration of y. We're trying to compare the distance traveled and average speed, But to do that, we're going to have to graph the same thing. So our relationship is that acceleration is the slope of the velocity graph. And since acceleration of object y is constantly at 6, that just means that our slope of the v graph for y would be 6. So you're gaining 6 meters per second of velocity every second. So that means that after 5 seconds, I have gained 6 meters per second 5 times, which gets me to 30. So actually, we can pretty easily compare here, because this would be our velocity of object y, and this would be our velocity of object x. So notice that, first of all, the average speed of y is clearly larger because the graph is higher up at all points except 0. And what about distance traveled? Well, distance traveled is just the area, and Vy also encloses a larger area. So makes sense that if they both start from rest, but object y has larger acceleration, makes sense that y will cover more distance and have a higher average speed. 1 star for this one. Also, you could have just as easily translated the other way and just said, well, x's acceleration is just going to be 4, so it's just a lower acceleration at all times. Either way works. A wheel of radius 0.25 meters and rotational inertia 6.28 kilogram meters squared about its center is at rest. We then give the wheel a constant torque of 8 Newton meters about its center. Calculate the linear speed of a point on the rim of the wheel after 1 revolution. Lots of numbers here, but notice I know things about torque and inertia, and it's constant. So if I have a constant torque, this is probably a forces Newton's second law idea. And it is, because remember, Newton's second law for rotation says that the angular acceleration of an object is equal to the net torque divided by the rotational inertia. So if we do that, the net torque is 8, and the rotational inertia is 6.28. And I know that's a very specific number. We'll see why I chose that in a minute here. And I was unprepared, and I need my calculator. 8 divided by 6.28 is 1.27 radians per second squared. So now that I have my angular acceleration, it says calculate the linear speed after 1 revolution starting from rest. So I don't know anything about time, but I do know a revolution. How many radians is that? That's 2 pi. So we can use the equation final speed squared is initial speed squared plus 2 times alpha times delta theta. So this means that our final angular speed would be the square root of 2 times alpha, which is 1.27, times change in theta, which is 2 pi. And actually, we see why I chose that weird rotational inertia, because that actually cancels with this. So I would essentially get 2 times 8 under the square root, which gives us 4 radians per second. So it's pretty reasonable to think, oh, okay, it's C. But it's not. We don't want the angular speed. We actually want the linear speed of a point on the rim. So remember that if you have sort of pure rotation or rolling without slipping, you can find the tangential speed using the fact that V is equal to omega r. So we have our angular speed, and we also have our radius. So we actually just get 1 meters per second. So we had to translate to linear here. So that's why I'd call this level 2. There's lots of numbers, but it's pretty straightforward with the chain of reasoning. All right. In the system shown below, each of the springs have the same force constant K. We have either 1 spring or 2 springs, and it says each time we just keep this mass stationary at its equilibrium position. We want to compare the effective spring constant of the system, and then we want to find the net force on the block in each case. So remember that we are combining springs, and we actually have a rule that says that springs in parallel is just going to equal the sum of the springs, because you're getting more and more extension. So each spring is helping to sort of share the extension. So you get the same force for less total extension because the springs are sharing them. All that's to say is that if this spring constant is K, this effective spring constant is 2k, because it has to extend less for the same force. So we know that 2 has a larger spring constant. What about the net force on the block? Well, it's saying the block remains stationary. So if the block remains stationary at each time, what does that tell you about net force? Well, it's equal to 0. Because if we look at our force diagram for each of these blocks, I don't care how many springs are attached. I know that there's going to be a gravitational force mg down, and then there's going to be either one spring force up or 2 spring forces up that are working together to cancel the weight. But either way, we're going to get 0 net force because we're at rest. So net force is the same. Spring constant is larger in system 2. I believe I called that 1. This is the first time I have to cheat. Yeah, I said that was level 1. I have my answer key in front of me so I don't make any mistakes. Just the letters, though. I can make tons of algebra mistakes, though, and we won't know. All right, a disk of mass m, radius r, and moment of inertia 1/2 mr squared. We have a string wrapped around it, and the disk is released from rest. The string unwinds. Calculate the angular speed of the disk after its center of mass has fallen a distance h. Well, anytime I see falling, I want to think about energy. So my relationship here is that my initial potential energy of the system is equal to the final kinetic energy of the system. And more specifically, since this is rotating and not slipping, there's 2 forms of kinetic. There's translational kinetic and there's rotational kinetic. So what this means is that we can set up our equation. It says the center of the disk has fallen a distance h, so its initial potential energy can be taken to be mgh. Kinetic energy translationally is of course 1/2 mv squared, and rotationally it's 1/2 I omega squared. And we want the angular speed of the disk. We want the angular speed of the disk, which means that we should get everything in terms of omega. And this is going to use the no-slip relationship from last time that we said that v without slipping can be written as omega r. It's that tangential relationship. So I can write mgh is equal to 1/2 m times omega r, quantity squared. And then my moments of inertia was 1/2 mr squared times omega squared. So now we can do some simplifying here, where we get GH, we'd get 2GH is equal to omega squared r squared plus 1/2 omega squared r squared, which means that we can divide both sides. Let's see, we get 3/2. So we get 2GH equals 3/2 omega squared r squared. So omega would be equal to 4/3 GH over r squared, all under a square root. And that is answer choice B. So as we could probably guess, there's a couple steps here. We got to connect linear and translational, and there's also the moment of inertia. We have these different energies. Of course, this is going to be our first like hard classification. An object is moving along the x-axis and it's subject to a force whose potential energy function is described by this, where A is a constant. Which of the following is correct about the equilibrium position associated with this force? So we want to find equilibrium and then talk about if it's stable or unstable. So, well, here we're going to use the relationship that F is equal to negative du dx, right? Because forces point towards locations of lower potential energy. So we're just taking the negative derivative of negative x squared plus 2ax, which is just going to be negative 2x plus 2a. So equilibrium position means that the force is equal to 0. So at equilibrium, there's no force. So that means that x is going to be equal to a. And is it stable or unstable? Well, that involves knowing the shape of the graph. So notice we have a minus x squared function here, which means that we are going to get something that looks like this. So that means that the point that we found is up here. And remember, a stable equilibrium means if I push away, the object will come back. Well, if I push an object from on top of the hill, it's just going to slide down and down and down and never come back. So when it's a maximum, it's actually unstable. So maxima are unstable. So this is B. Because you had to figure out unstable from the function, I bumped this to 2. A block of mass m is attached to a spring. The spring is displaced a small distance in the minus x direction before being released from rest. If there is a kinetic coefficient mu, which of the following differential equations describes the motion of the block when the block is moving in the plus x direction? So we're going to look at the moment in time where the block is moving to the right. So notice that if we have any sort of differential equation, we know it's going to be some variation of net force is equal to mass times acceleration. That's sort of our goal here. So if we look at what's going to be happening, what's happening to our block, while we're moving in the plus x direction. If we're moving in the plus x direction, we know that our frictional force is going to be opposing that sliding, right? If the mass is sliding to the right relative to the ground, there's going to be a frictional force to the left. And then always, we know that since the equilibrium position is x equals 0, we also know that F of the spring is equal to minus kx. So we know that there's also going to be some sort of a spring force that may or may not be directed that way, but if x is positive, it is. Now that's sort of encapsulated in the direction. So what differential equation is it? Well, this is like energy. So this is clearly not forces. Those are energy-related items. So we can see that I'm always going to have a spring force that opposes my position. So that's why that is always negative kx. And if I'm moving in the plus x direction, the friction is going to act in the minus x direction. So it'll actually be choice D. What did I call that? I called that level 2. Because I think you could probably just assume that this frictional force had to be opposing the motion. A group of students wish to calculate the acceleration due to gravity using 2 masses and an ideal pulley. The students record the acceleration of the system A for various combinations of masses. What can be graphed to form a straight line to solve for G? Well, this is your classic Atwood. Many of you have probably done this as a lab, but we want to relate the acceleration to these 2 masses. So as per usual, just like I always like to do with systems, unless if we're interested in the internal forces, is we make it into a big box. And there's no friction. So that means that the only thing that is sort of external to the system that is creating an unbalanced force would be the weight of m2. So now we can use our simplified Newton's second law for systems that says the acceleration of the system is equal to F net on the system divided by the total mass of the system. So F net on the system is mg for the hanging mass, and the total mass of the system is m1 plus m2. All that is to say that the acceleration can be written as g times the quantity m2 over m1 plus m2. So this means that this can be my y-axis, and this can be my x-axis, and the slope is g. I called this level 1. Even though there's some deriving, this is a pretty standard result. Four identical masses are placed along the squares shown below. We're just rotating the square about different axes. So when the square is rotated around the first axis, the rotational inertia is I. What is the rotational inertia around this sort of diagonal axis? So rotational inertia is the sum of all the mr squareds, where we're taking r to be the perpendicular distance from the axis. So notice that in axis 1, due to symmetry, I have just 4 point masses that are just half the square length away. So my moment of inertia could be found as 4 times m times s over 2 quantity squared, which would be which would just be m times s squared. Now, what about axis 2? Well, it's the same idea. Except now, this axis actually kills 2 of the masses because they have no perpendicular distance. They're on the axis. So this means instead, I have 2 masses that are rotating. They're of mass m. But what's this distance perpendicular to the axis? Well, it's half of the square diagonal, which would be 1/2 of s root 2, right? Because by Pythagorean theorem, the whole diag is s root 2. So this is just half of that. So we get s root 2 over 2 squared. So we get 2 times m times s squared times 2 divided by 4. And notice that this is just a half, and the half and 2 makes 1. So it's actually the exact same. So even though you took out 2 of the masses, you also extended the distance to the remaining 2, and the quadratic effective distance totally balanced it out. That's kind of a nifty one. It's not necessarily obvious that it'll be the same. I consider that level 2 because of that diagonal idea. A 2 kilogram block is sliding down a ramp that makes a 345 angle, 36.9 degrees as shown. Given that there's a kinetic friction coefficient of 0.25, calculate the magnitude of the net force on the block. Well, this is our classic ramp setup, where we have part of the gravitational force sending you into the ramp, and we also have part of the gravitational force pulling down the ramp, and then the normal force must exactly balance the into the ramp component. And then since we're sliding down the ramp to oppose sliding, there must be a kinetic friction force pointing up the ramp. So this means our net force is going to be the helping forces minus the hurting forces. So what's helping it accelerate down the ramp? Well, that's going to be mg sine theta. What's going to hurt it? Well, that's going to be the friction force. So what is friction force? Well, friction is mu times the normal force, which is mg cosine theta in this case, right? Because the normal force balances the into the ramp part. So that means that my net force can be written as mg times sine theta minus mu cosine theta. So let's see if we can work that out here. So mg, well, my mass is 2 kilograms, so mg would be 2 times 10, which is 20. Sine theta, this is the 345 angle, and it's the smaller one, so this would be 0.6. And then this would be 0.25 times 0.8, which would be 0.2. So we get 20 times 0.4, and that's where I struggle, and I get 8 newtons. Again, I knew this in my head because I know that 36.9, that's the 345 angle. So that means the cosine leg would be 4 and the vertical sine leg would be 3. So that's how I knew my trig ratios there. Now, of course, please use your calculator. I still called this level 1. This is a like pretty standard general physics question. A ball is kicked into the air at a velocity v, oriented 60 degrees above the ground. What's the maximum height reached? So you can use this with energy or kinematics. I actually think this is a lot easier with kinematics. If you did this with energy, you'd have to set kinetic at the bottom equal to gravitational at the top plus kinetic at the top. Because since this projectile is angled, it doesn't stop at the top, so you still have kinetic at the top of your trajectory. You will get the same answer. So the maximum height is determined when the y velocity is 0. So whenever you have angle, the first step is always to decompose, right? The x component would be v cosine 60, which we don't actually care about. And the vertical component would be v sine of 60. So this actually tells us that the initial y velocity is equal to root 3 over 2 times v. So now we can just do kinematics. So we want how high does it go? Notice we don't have anything about time, so we want to use the timeless kinematics. So we know our final y velocity is 0. Our initial y velocity is root 3 over 2v. Our acceleration is g, technically g down. And our delta y is that height h we wish to calculate. So we get 0 equals 3/4 v squared minus 2gh. So we'd get 2gh equals 3/4 v squared. So h would be equal to 3v squared over 8g. And that is an answer choice, that is B. I'd still say this is level 2. The component aspect of this makes it work. There is also a shortcut formula you might remember with maximum height. It's this. There's like a projectile formula that says the maximum height reached by a projectile is v0 sine theta squared divided by 2g. Which is cool, I guess. If you have that in your brain, you could use that, and that kind of trivializes this. You will see that it's the same answer, but this is how you sort of get that result. A ball of mass 0.6 kilograms is attached to a string. The string has one end attached to the ceiling, and the ball is swung in a circular path of radius 1.2 meters at a constant speed of 4 meters per second. Calculate the tension in the string. So, notice that this tension force is sort of doing two things. So the first thing the tension force must do is the tension is at least supporting the weight of the ball. So the tension force has to support the weight of the ball somehow. But then also the tension force has to be supplying this centripetal force that keeps us going into the circle. So there's also this sort of centripetal force mv squared over r. So we have to just account for both of those effects. So we'll do that. So first of all, and these meet at a right angle. So I'll call these directions x and y. I'll call like the centripetal x and the vertical y. So we know that the tension in the y direction is just going to be mg, which is going to be 6 newtons, because it has to balance the weight of the ball. And then for the tension in the x direction, it's supplying a centripetal force. So that must be supplying the mv squared over r. And we're given m, v, and r. We're given 0.6. V squared is 4 squared. And r is 1.2. So that's just going to be half of 16, which is 8. So we have 6 newtons and 8 newtons. So this means our force triangle essentially looks like this, where we have 8 newtons centripetal, and then we have 6 newtons perpendicular to that. So that, of course, means that we can find our net force just using Pythagorean theorem. So T is just the square root of 8 squared plus 6 squared, which is 10 newtons. This is a difficult level 2. So a couple things going on here. There's definitely harder variations of this conical pendulum, but there's a couple steps here which makes it clearly at least level 2. All right, consider the following scenario involving 3 observers. Observer B is on a skateboard moving in the x direction. They drop a ball downward relative to them, and A and C are just looking. Which of the following compares the magnitude of the velocity's x component of the falling ball from each observer? So what's important is that in B's frame of reference, B is moving. B is moving, and they drop the ball in their frame. So B is not going to measure the ball moving left and right relative to them, right? If you're sitting in a car and you drop something, it's going to drop straight down in that car. So we actually know that the speed as measured by B is equal to 0. And then A and C, well, they're going to see the ball just falling in the plus x direction horizontally, and they're going to agree on that. And actually, there's only one choice that has B ranked last, and we know they're not always going to be the same. So we get C. Most of these relative velocities are a pretty easy level 1. So A and C would measure that sort of parabola trajectory, where B just sees a line going straight down. All right, let's see. We're going to do a quick time check. Not bad. A solid sphere with mass m, radius r, and rotational inertia 2/5 mr squared about its center rolls up a ramp that makes an angle theta with the horizontal. Assuming the sphere rolls up the ramp without slipping, what is the force of static friction exerted on the sphere by the ramp? Okay. Well, first of all, notice that the rotation of the sphere is going this way. To roll up a ramp, it has to be rotating that way. So what that means is that if it's rolling up a ramp and is getting stopped by friction, the frictional force must be trying to slow the rotation. And the only way you can slow the rotation is by applying a frictional force up the ramp. Alternatively, you could say, oh, well, the bottom of this bottom point here is stationary. And if I released this stationary point and allowed it to slip, it would fall down the ramp. So friction must point up the ramp. Either way, we know there's going to be a friction force up the ramp. And then since we are just on a ramp, we know that when we're on a ramp, we have a weight component, mg sine theta, that tries to pull us down. So this means that our net force equation can be written that the net force is equal to, we'll say that doesn't really matter. It's going to be accelerating down the ramp. So we'll say F net is mg sine theta minus F friction. So we can rewrite that, since F equals ma, we can say that ma equals mg sine theta minus F friction. So that's one equation. And then also, we know that there's a torque being applied. The torque is being applied to the sphere at the bottom. So the net torque is caused by friction, and that's a distance r from the axis of rotation. So we can say I alpha, where I is 2/5 mr squared in this problem, is equal to Fs times r. So now we can start combining things, because we know there's no slipping. And if there's no slipping, since I want to solve for F friction, it's probably easier to eliminate one of the accelerations. So I can say that the alpha is equal to A over R, using the no slip condition. So this means 2/5 mr squared times a over r is equal to static friction times r. So notice that's going to eliminate all of the r's because I get 2/5 ma is equal to the static friction now, or acceleration is equal to 5/2 times the static friction force divided by the mass. All of that allows us to plug in. So we said that acceleration is 5/2 static friction divided by mass. So we get 5/2 times the static friction force is equal to mg sine theta minus the static friction force. So I can add that friction force to both sides and get 5/2 plus 2/2, which is 7/2, times the static friction force is mg sine theta, which means that the static friction force is equal to 2/7 mg sine theta, and it's directed up the ramp. This is on my short list of being among the hardest on the whole test. Just an FYI. I included this because there's a very hard question like this on last year's free response. The direction alone is hard enough. All right. A beam of mass m is uniform along its length L. The beam has supports at x equals 0 and x equals 3L divided by 4 as shown. What's the largest position that a person of mass 4m can stand before the beam begins to tip? Well, if the beam begins to tip, that person is going to end up being over here somewhere. Because that means they're applying so much torque to the right of the supports that this end is just going to start flipping over. So we're going to actually pick our pivot point to be this second support right there. Because if the beam starts to rotate, this end is going to lose contact. So there's going to be no normal force here that we have to consider. So we're going to say that this person is going to exert a force 4 mg down. And then this is a beam with mass. So there's also going to be a gravitational torque mg caused by the beam. So this distance we know. This distance, it's, well, what's the distance from 1/2 to 3/4? Well, that's going to be 1/4 of the length. And what's this distance? We don't know it, so I'm going to call this distance d. So if the torques are equal at that moment, we know that mg times L over 4 is equal to 4 mg times d. The mg's go away, and this says d is actually 1/16 L. And if we notice how we define d, d is the distance away from this 3/4 support. So this means your position x is just going to be 3/4 L plus that tiny extra distance 1/16. And since 3/4 is 12/16, we get 13/16 L. I'll be consistent and make this that color. Level 2. Static equilibrium. You had to notice that it was, actually no, I did put all of them to the right of the pivot point. Spherical planet with radius r has uniform mass density. The field strength is g at the surface. What's the field strength halfway through? So our relevant expression is that the gravitational field strength is g times the mass that's beneath you divided by your distance from the center squared. This is a shell theorem idea, or Gauss's law if you're an E&M person. So we're interested in what is the field strength if I'm sort of halfway out. So also remember that if we're inside this planet, we're sort of gaining mass, right? Because I get more and more mass as I go out. So m is going to be proportional to volume, which is proportional to distance cubed. So if I do this, my gravitational field is going to be g times m divided by r squared. So my m, if I'm halfway out, I have only 1/2 cubed, which is an eighth of the mass, divided by r squared, and I'm halfway out, so that's 1/2 squared. So maybe I should write this as 1/2 cubed to show the dependence. So I get 1/2 cubed divided by 1/2 squared, which is just equal to 1/2. And now there is a nice shortcut for this that doesn't involve this result, because actually remember, if you're inside the planet, gravity is actually linear. Field strength is actually linear inside the planet. So because of this result, because you gain mass at a cubic rate, but field drops off at a quadratic rate, you actually get this very interesting plot of gravitational field strength as a function of r, where this maximum is the planet radius. So that's tricky. I give that 2 stars because people do recognize this idea that gravity is linear inside the planet. People sometimes remember that, or if not, that's how you derive it. All right, we have a 2-block collision here. The blocks are colliding, and the force on block 2, which is initially stationary, is described as this f of t, and we are interested in the final speed of block 1. Well, anytime you have force and time, we know this is an impulse problem. So, impulse, we know actually that the change in momentum, I'll use black, the change in momentum for block 2 is just the integral of the force with respect to time, because you add up all of the force times time contributions, that gets you your total momentum change. And we're given this kind of odd function, mv0 over capital T squared times t from 0 to capital T with respect to little t. Most of these things are constants, however. So the m, the v0, and capital T are all constants. And this is a pretty standard antiderivative. You just get capital T squared over 2. So we get our momentum change of block 2 is 1/2 mv0. And why that is helpful is because we were asked what's the final speed of block 1, but this does relate, because by Newton's third law, or momentum conservation, we actually know that delta p of block 2 is the opposite of the delta p of block 1. Because if the total momentum can't change, any momentum lost by block 1 must be gained by block 2, or vice versa. So actually, we know that delta p for block 1 is just the negative of 1/2 mv0. And what is that going to be? Well, block 1 has mass m. We don't know its final velocity, but its initial velocity was mv0. So everybody brought m, so the m cancels, and we just get negative 1/2 plus 1, which is just positive 1/2. So the final velocity is just 1/2 v0. I would actually call this hard, because you have to do that third law connection. If you solve for the speed of the wrong block, you do get a different number. And also, if you mess up the sign, you get the distractors. So I would confidently label this as a level 3, because there's calculus and Newton's laws and a whole bunch of conservation stuff. A car starting from rest experiences a uniform acceleration in the plus x direction. Which of the following pairs of functions could describe the position and velocity of the car? So the car starts from rest, so we know that v of 0 is equal to 0. And we also know that acceleration is uniform, which means that acceleration is a constant. So the only thing so first we can eliminate the quadratic v's, because if I take a derivative, it's not constant. Also, I can eliminate this velocity function, because it is not a velocity that starts from 0, so by elimination, it has to be this one. Level 1. If you look at which one looks like a kinematics equation, it's going to be C or D, and then you know it starts from 0. Not too much to say there. All right, we got 2 beams. They're connected at this L shape. One of them is horizontal and has uniform mass density, and the other has a density function, and it's longer. So we know the one with uniform mass density. We can just plop a center of mass right there for that beam. And we need to find the center of mass of the other beam, which is not uniform, so it's going to be somewhere over here. And then the center of mass is going to be somewhere on that line connecting the two. So we have to somehow find the center of mass of the non-uniform beam first. So the y-coordinate of the center of mass is defined as 1 over the mass of the beam times the integral of y dm, where this quantity dm, this change in mass, is mass per length lambda times change in length, which is dy in this case. So our lambda function was 3m over 8l cubed times y squared. So we can pull some things out of the integral. 3 can come out of the integral. 8l cubed can come out on the denominator. And this beam has length 2l, so we got to integrate up to there. So just kind of going on autopilot here. Doing our little power rule. So we get 3 times 16l to the 4th divided by 32l cubed. And that's going to be 3/2 L. So that's just to tell us that this coordinate right here, this is actually at y equals 3/2 L. And this is at y equals 0. So we're asked, where is the center of mass of this system? Well, half of the mass is at 0, half the mass is at 3/2 L, so we're just going to take an average. So y of the center of mass is just going to be 0 plus 3/2 L, all divided by 2, which would be 3/4 L. So no surprise here, this is a 3-star all the way. Due to that calculus, and then the multi-step where we had to shrink both of these to points and average them. So that's still a bit tricky. A disk is initially at rest and is not rotating. Consider the following scenarios that we apply a net torque that increases the disk's angular speed. We're given the angular speed at the end of scenario X, which is omega. We want the angular speed of the disk in scenario Y. So we're given torque as a function of time. So if we're getting torque and time, this is impulse momentum, but for angular. So my change in angular momentum is equal to the integral of torque with respect to time. And that's, of course, just the area under the curve. And since change in angular momentum is just going to be I omega final minus 0, we're just really looking for the area. So we're just comparing the areas. So if one of these curves has double the area, it's going to result in double the final angular velocity. So in scenario X, this is just a triangle. This triangle has base 4 and height 4. So 1/2 times 4 times 4 gets us an area of 8 in quotation marks. It's really 8 RFT. And then scenario Y, well, we have to be a bit clever with these areas if we want. We can split this into a triangle, and a rectangle if we want. So the triangle is 1/2 times 1 times 4, so this is a 2. By symmetry, this is also a 2. And then this has a base of 2 and a height of 4, so this is 8. So this area here would be worth 8, and this area here would be worth 12, and 12 is 3/2 as much as 8. I'd call this level 2. Now the square root is for thinking this is some sort of energy ratio. So if you picked a square root answer, you thought this was about work and not impulse. block of mass 0.1 kilograms moves at 0.4 meters per second in the plus x direction towards a block that's going to hit it in a head-on collision. The blocks collide and stick together. What's the velocity of the center of mass after the collision? So you could just do the VCM formula and be done with it, because in these problems, VCM stays constant. But actually, if these stick together, they're going to have a shared velocity that is the center of mass velocity. So I'm going to do this with momentum. If you like the center of mass approach, you can totally do that. It's equivalent. So I'm going to say that the momentum before equals the momentum after. So the momentum before the collision would be 0.1 kilograms moving at +4, and it's going to be added with 0.4 kilograms moving at -3. And then after the collision, it's just going to turn into a big lump of mass of 0.5, moving at some velocity v final. So if I were to go compute these, this is positive 0.4, this is negative 1.2. So I get negative 0.8 is equal to 0.5 times the final velocity. So the final velocity is just 8 divided by 0.5 with a negative sign, so negative 1.6 meters per second. And that gets us answer choice B. Makes sense that the answer is negative x because this is our momentum winner. It has basically the same velocity, but more mass. So of course that one wins. I said this was level 1. This is also a general physics question. A bucket is attached to a rope and swung at constant speed in a vertical circle, as shown. Which of the following is correct about the tension in the string at each of the locations? So we're comparing the tension force. So what we know is that it's swung at a constant speed in a vertical circle. So if it's at a constant speed, we know that the centripetal force, which is mv squared over r, is a constant, which is also the net force. So we need to see what needs to happen to maintain net force being constant. So at location 1, we have a tension force pulling up, and at location 2, we have a tension force pulling down. But this isn't just a bucket that exists in a vacuum. There's also a gravitational force, which always points down. So notice that at location 2, gravity is sort of helping the tension. So the tension doesn't have to pull as hard at 2 because gravity's helping it. Whereas in location 1, the tension has to pull much harder because it's fighting gravity as well. So the tension has to be bigger at location 1 because the tension force and weight of the bucket are in opposite directions. I think I called that level 2 because the comparison was not trivial there. And I need to sneak a peek at my key. What is this, 25? Yeah, 25, I said 2-star. 26. A planet is in circular orbit around a star. The kinetic energy of the planet is K, the gravitational potential energy of the system is U, and K plus U is E. Calculate the ratio U divided by E. Okay. Well, we should probably get an expression for E. So E for the system is 1/2 mv squared plus the gravitational potential energy, negative gmm over r. But also, we're given that we're in circular orbit. So if we're in circular orbit, the gravitational force, gmm over r squared, has to exactly balance, or sorry, has to supply a centripetal force, mv squared over r. So that actually means that when you're in circular orbit, v squared is equal to gm divided by r. So what that does for us is that allows us to actually get rid of v in this expression. And notice we have a half gmm over r minus 1 gmm over r. So we actually get negative 1/2 gmm over r is the total energy. So if we were to compute U divided by E would be equal to negative 1 gmm over r divided by -1/2 gmm over r. And that's actually equal to +2. So lots of weird things going on with this, with the signs and like total energy being negative because of the bound system. Absolutely level 3. Energy in orbits is tricky. That's a tricky one for sure. A cylinder of mass m and radius r is spinning at omega naught around an axle, and then we drop a cylinder of the same mass but twice the radius on top of the original cylinder as shown. What's the final angular velocity of the system? Whenever you see this picture, you should know it's conservation of L, right? This is a pretty standard angular momentum picture. There's some weird stuff going on here because I don't really give you the rotational inertia, but it does not matter. So this is conservation of angular momentum. So we know that the initial angular momentum equals the final angular momentum. Now the initial angular momentum is just going to be the initial moment of inertia times omega naught, and the same thing here, except it's final. So we really just need to figure out what's going on with the moment of inertias. Now, it doesn't actually matter what shape constant you use because it's the same shape every time. What we do need to remember is that the moment of inertia is equal to like some shape constant times mr squared, or really we want to know that I is proportional to r squared. So if this disk had moment of inertia 1, attaching a disk of the same mass but twice the radius would have rotational inertia 4. So this actually means that this rotational inertia of the system would be essentially equal to 5, whereas this rotational inertia is equal to 1. So if you multiply the inertia by 5, so we know this must be constant. So if I multiply the rotational inertia by 5, I must be multiplying the angular velocity by 1/5, or dividing by 5, in order to compensate. So it's actually 1/5. Now, if you just knew the result for a hoop or a cylinder and just started plugging and chugging, you would get the right answer. But here's like a sneaky ratio way of doing it. 2 star, borderline 3, but I'd call it 2. 3 stationary blocks are connected in a rope train like this. Which of the following is true about tension forces in the rope? So we want the tension in rope 2. We also want the rope with the greatest tension. So once again, the big box is your friend whenever you have lots of things connected to each other. So what's the tension in rope 2? Well, this entire system is stationary. So notice that if I put everybody below, if I put everything attached to rope 2 in a box, this tension is internal. So this tension cannot contribute to the net force. So what that must mean is that essentially rope 2 is existing connecting to a mass of 5m. So rope 2 is supporting a mass of 5 mg, or a mass of 5, so it has a weight of 5 mg. And by similar argument, rope 1 is supporting everybody beneath it, so it has to have the highest tension. So that would be C. I would call this clearly level 1. It's really just a Newton's third law idea where these tensions are going to be pulling in opposite directions on adjacent masses. So all you're looking at is what is the total mass below each rope. All right, kind of an interesting one here. A model rocket of mass 1.2 kilograms is launched from the ground at 20 meters per second at a suspicious 345 triangle angle above the ground. Once the rocket reaches the top, it explodes, causing a 0.8 kilogram chunk of the rocket to fall straight down. We want the speed of the 0.4 kilogram piece directly after the explosion occurs. Okay, so this is going to combine a couple ideas. It's going to combine projectiles and momentum center of mass ideas. So the key here is that the explosion is actually occurring at the top. So what we know here is that when we're at the top of the trajectory, the rocket does not have vertical speed. It only has speed in the x direction. So that means that we just need to figure out this horizontal velocity before we start dealing with the momentum aspect of this. So this is a pretty standard projectile launch. We were given that its speed was 20 meters per second. So if we were to go decompose this, we're only interested in the x velocity today. And this is just going to be 20 times cosine of 53.1 degrees. And if you type that in, this is the 345 angle where it's the lower of the two. So this would be 3/5 or 0.6. So this is going to be 12 meters per second. So what that tells us is that at the top of the trajectory, before the explosion, the rocket is moving at 12 meters per second. But then it explodes. So we have to deal with momentum conservation. So we know that the momentum before the explosion horizontally has to equal the momentum after the explosion horizontally. So before the explosion, we have the entire 1.2 kilogram rocket moving at 12 meters per second. But after the explosion, we have the heavier 0.8 kilogram piece. Well, that's falling straight down, so it has no horizontal momentum. And we have a 0.4 kilogram piece that's at some new Vx. And if we work this out, or you can just kind of eyeball it, well, notice that the mass of your system that's moving horizontally went from 1.2 to 0.4. So if you third the mass, you're going to have to end up tripling the velocity to get the same momentum. So our new velocity would be 12 times 3, which is going to be 36 meters per second. And that is an answer choice. Notice you can see how you get the distractors. So you can pick the wrong trig angle. So like the 345, this would be 16 meters per second if you did the vertical. And then if you tripled the wrong one, you get 48. Yeah, this is hard. This was hard. The distance between the pieces when they land, I originally had that, and that was just an insane problem to ask for multiple choice. The original question asked, like, how far is this piece from this piece? And you had to put range into it. It was an absolute mess. But this is a neat one. It combines momentum and projectile component stuff. So pretty neat there, but still level 3 for sure. Mass on a spring oscillates with maximum displacement A from equilibrium. We have the following two energy diagrams that are shown below. So we have an equal share, and then we have an unequal share of energies. Which of the following could represent the energy distribution of the mass spring system when the mass displaces the spring half the amplitude? So we're talking about force and we're talking about energy. So we probably want to look at the energy approach as our justifications. So A over 2 from equilibrium. So remember that our relevant formulas are that spring force is equal to K delta X, whereas spring potential energy is equal to 1/2 K delta X squared. So notice that when delta X equals 1/2 A, US is going to be 1/2 times K times 1/2 A squared. So we're actually squaring the 1/2, so that's essentially a multiplication by 1/4. So the fact that we have half the displacement doesn't mean we have half the possible spring energy. It actually means we have 1/4 of the maximum. So the correct diagram is going to be 2, because elastic potential energy depends on displacement squared. So even when you're halfway out, you're still only having 1/4 of your energy budget in the spring potential. Because notice I say it's 1/4 because I could have potentially having all 3 of those kinetic bars given. So you only get 1/4 of your energy budget there. So I gave that 2 stars because it's not trivial. You do have to reason through the dependence there. It's definitely an easier level 2. All right, a bullet with horizontal velocity v impacts a wooden crate that's hanging from the ceiling. We have 3 possible outcomes. We could get stuck in the crate, we could pass through the crate unfazed, or we could bounce off the crate. And we want to rank the impulse delivered to the crate in each collision. So the crate is kind of difficult to analyze, so we'll have to use Newton's third law. Because remember, anytime you have a collision, the forces are equal and opposite, and the times are the same. So that means impulses are equal and opposite. This is also a consequence of momentum conservation. So we're just ranking m delta v for the bullet, because impulse is m delta v. So in case 1, the bullet becomes lodged inside the crate. So we know its momentum is going to change, but it's also not going to totally stop the bullet because the crate's going to be moving to the right. So we know we get some sort of impulse. It's less than the original momentum of the bullet because the bullet doesn't stop. Collision 2. I pass through the crate, come out the other side at approximately the same speed. So my momentum is approximately the same. So I don't really experience an impulse. But if you bounce off the crate, that means not only did the crate have to stop you, so not only did you have to steal its original momentum mv, you also had to give it some momentum in the rebound. So this actually gives you a momentum that's larger than its original one. So we can see here that you essentially get 0 momentum change in collision 2. So that should go dead last. And then also you get a large momentum change in collision 3. So that leaves us with A. This is a level 2. I think this might be my favorite question on the whole test. If there's any teachers watching, you can really see this as the pumpkin question from AP1, where an archer is shooting an arrow at a pumpkin. That was sort of the predecessor to the QQT. That's a really fun free response. The top of a hoop of radius given is nailed to the ceiling as shown. When the hoop is displaced a small distance and released from rest, what is the period of small angle oscillations? So this is a pendulum, but it's not a mass on a string pendulum. It's a physical pendulum. So we have to use the formula. Period of a physical pendulum is 2 pi times the square root of I pivot divided by mgd. Okay. And we have a hoop. So what does a hoop tell us? Well, all of the mass is distributed away from the radius in a hoop. So that means that the moment of inertia of the hoop about its center is just a point mass 1/2 mr, or just regular mr squared. But we did not pivot the pendulum about the center. We pivoted the pendulum about the top. So we have to use parallel axis theorem. That says the new rotational inertia is the center of mass moment of inertia plus md squared, where d is the distance from the center of mass. So we just go out another radius. So parallel axis theorem gives us 2 mr squared. So our pendulum has period 2 pi square root 2 mr squared divided by mgr, because r is our distance. In this case, a bunch of stuff cancels, so we get 2 pi times the square root of 2r over g. So we get 2 pi times the square root of 2 times 0.45 divided by g. So we get, let's see what that is. We get 0.9 divided by 10, square root that, multiply by 2 pi, and I get 1.88. So I get 1.9. This is definitely level 3. The parallel axis theorem component is what sends it over the edge. Consider the following arrangements of 3 asteroids on a line. We either do 1, 2, 3 with the m's, or we do 2, 1, 3 with the m's. we are interested in comparing the net force on the lowercase m, or sorry, on the single m mass, and then we want to find the comparison of U for the system. So first for forces is pretty straightforward, because in configuration X, we see that we essentially have a force of 2 going this way, and then we have a force of, the mass is tripled, but the distance is doubled, so the square law gives us 3/4. So we get 2 plus 3/4 kind of for the force in the X. But then in configuration Y, we see that the attractive forces are going to cancel each other, where we have a 3 and a 2, but they're fighting. So the net force is larger in X because we have 2 attractive forces, and in Y we have the same 2 forces essentially, but they're fighting each other. So we know that the force is larger in X. And then what's going to go on with our energies? Well, for our energies, remember we have to take sort of this pairwise sum where it's negative gm over r. So U is equal to the sum of negative gmm over r. So this pair is worth -2. This pair is worth -6. And the cross pair would be worth -3/2. So we can already guess that X is going to be much more negative because the bigger masses are centrally located. But if we look at configuration Y, just to check, this pair is worth -2, this pair is worth -3, and the cross pair is worth 6/2, which is -3. So configuration X is going to be a more negative number. So for the net force we said was going to be bigger on X, and the gravitational potential energy is more negative in X. Now remember, potential energy, more negative means you're more tightly bound. So it makes sense that X is more negative because this is a more attractive system than this. So it makes sense that X is more negative. Oh, that's level 2. That's level 2. Anything with the sign of potential energy is hard. A block is moving in the direction, all right? It's moving along a frictionless surface before colliding with a spring. Which of the following is true about this collision? So it is a collision, but there's a spring involved. So usually we lose kinetic energy in collisions because there's some sort of non-conservative force happening. But here, if there's a spring, there's no way for your energy to be lost in the form of light and sound in a non-conservative ways because the spring force is conservative. So this is just a pretty basic recall idea that springs are conservative because remember, we have an expression for U. If you have a potential energy function, you are conservative. So U spring is 1/2 kx squared. So this means that we can always account for our energy. So the kinetic energy isn't necessarily constant at all times, but before and after the collision, the kinetic energy is the same. Like there is a moment where kinetic energy is being converted to spring potential there, but it eventually all comes back. And this is just obviously not true. Kinetic energy is not conserved in any collision. Total energy is, but it might not be in useful forms. A pulley of mass m and radius r has rotational inertia I. 2 masses are attached by a string to the pulley. The system is released from rest, and the pulley experiences an angular acceleration alpha about its center. Which of the following equations are not necessarily true, given that the tensions in each string is labeled? So this is definitely some net force and net torque equations and some rolling without slipping ideas. So we have tensions that are acting on the masses. So maybe we can write just all the equations and sort of cut them out of the list when we establish them. So notice that this is a larger mass. So we know that the system is going to accelerate this way. So I know that my net force on the M is equal to the tension that's helping the M move in that direction minus its weight that's fighting the motion. So given the fact that acceleration is alpha times r, using the no slip condition, we see that we exactly acquire d. So that works. Then from a similar argument, we can do the net force on the mass of 2m, where the 2mg is helping the system accelerate and the tension in the string is fighting. And by the same argument, we acquire choice C. So now for A and B, we're just going to look for sort of what's happening to the pulley. Well, notice the pulley is going to get rotated by the difference of these two tensions that are supplying torques. So for the pulley has rotational inertia I, and the net torque acting on the pulley would be the 2m tension helping it rotate minus the 1m tension fighting its rotation, and both of those forces are applied at a distance r from the center. And notice that it's exactly equation B. So what A is doing is A is essentially taking some F equals ma equation, but doing it with the pulley, and we can't do that unless you get a very specific rotational inertia. So this is level 3 because we have to do so many different analyses to eliminate this stuff here. Next, a hollow sphere with mass m, radius r, and rotational inertia 2/3 mr squared is not rotating. We launch the sphere at v0, and it is eventually going to start rolling without slipping. We want to find how long that takes. So this is another hard question about connecting linear and rotational dynamics. So when we're actually accelerating, we know that the net force is going to be supplied by kinetic friction because we're moving too fast for rotation at this point. So we're going to be skidding. I believe that's the right word. The bottom point is going to be moving too fast, so there is going to be a leftward friction. So that friction does two things. The friction is going to slow the translation, and it is going to speed the rotation. And eventually, those two effects will exactly balance, causing the slipping to stop, and we get a nice constant velocity. So we can just set up a net force and net torque relationship. So for the forces, we know that the net force is going to be the forces helping the translation, which is 0 forces, minus the forces fighting the translation, which is kinetic friction, which is just going to be mu times the normal force, which is mg, because we're on a flat surface. So my acceleration is just going to be negative mu times g. And as a result, this means the velocity, translationally, can be found by taking our initial velocity and subtracting off mu g times the number of seconds it's been sliding for. And similarly, the net torque about the center is going to be equal to the frictional force causing the rotation, and that is applied at a distance r. So we get our rotational inertia, 2/3 mr squared times alpha, which is equal to Fk times r, and we actually do know what Fk is. Fk is mu times normal force mg. So we get our angular acceleration is going to be 3/2 mu g over r. So this means that our angular velocity is just going to be 3/2 mu g over r times t. So now what does it mean to not slip? Well, what it means to not slip is that the angular and linear velocities obey the relationship v equals omega r. So this means v0 minus mu gt is equal to 3/2 mu g over rt times r. So we would get v0 equals, we just add another mu gt to that, we get 3/2 mu gt. So t would be equal to 2/5 times v0 over mu g. Lovely. This is also up there. This is also up there for one of the hardest ones. And this also just kind of looks wrong, because this looks like that shape constant for the non-hollow sphere. That's a tricky one in there, kind of right at the end, because you had to be able to do force analysis both ways, and you had to set them equal. A satellite is in orbit around a stationary planet. Given the total energy of the planet-satellite system is positive, what can be said about the shape of the satellite's orbit with justification? So we're given that kinetic plus potential, which is the total energy, is positive. So what this means is that no matter where you are, you're always going to have some sort of kinetic energy, because in orbit, gravitational potential energy is always negative. So no matter what, you're always going to have sort of more kinetic energy than gravitational potential energy, in magnitude at least. So that means that the kinetic energy must always exist. So no matter where you are in this orbit, you're going to have some sort of kinetic energy, even if you are very, 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 very far away. So what this actually means is that we're actually going to get an escaped orbit. This is a hyperbola, an escaped orbit, because we're allowed to go infinitely far away. Because the only reason we get trapped in an orbit is because our total energy is negative. So this is a nice shortcut, is that if E is less than 0, your orbit is bound, meaning you're trapped. Because no matter how fast you go, you're always going to be stuck with this negative amount of total energy. So you can't get super far away. You can't get all the way to infinity. Notice you can get to infinity in this case, because if I cross off the negative, I do have positive equals positive, which works out. But if my total energy was negative, I would get a contradiction, because I would get positive equals negative, and that can't happen. So this is tricky. This gets 2 stars, even though there's like no work that's involved. This is very tricky. So you can get very, very, very far away, because it's possible that even when you have 0 potential energy in this system, you will still have positive kinetic. Planet X is spherical with radius r. The period of a simple pendulum is t0. At the surface, what's the period and altitude r above the surface? We want to take this ratio of the r's. So we're really comparing the pendulum period if we're at the surface versus another r from the surface. So to do that, we know what the period of a pendulum is. The period of the pendulum is 2 pi square root L over G. But also we got to figure out how G changes. So we actually know that G is equal to GM over R squared. And in this case, we are doubling the distance from the center of the planet. We're going from R to 2R. So this means that the new G is actually just a quarter of the original G. So this means my new period is just going to be 2 pi times the square root of L over G, where this G got multiplied by a quarter. So this means that our new period of rotation is just, or of oscillation, is just square root of 1 divided by a fourth. So that's just 2. This is a pretty standard question, so I would give it a 2 star. But there are some subtleties going on here. You have to be able to find the new G. A block of mass m falls from rest in the minus y direction. There's a drag force in the plus y direction. Which of the following can be solved to get v as a function of time? So we have some scary looking integrals here. So we're given that we're falling in the minus y direction. So we have a force mg. And it also says we have a resistive drag force, kv, that's up. So if we want a differential equation, which is what's going on here, we know that we want to write F equals ma. So we know that F net is equal to the forces helping us move, mg, minus the forces fighting us moving, kv. F net is ma, which is dv dt. Solve for dv dt, and we get dv dt is equal to g minus k over m times v. And then from here, we can just separate. Notice I have to move literally everything because I have no way to get this. I can't get the dv term with just the k over mv. I have to divide by the entire expression to separate. So I have to get dv divided by g minus k over mv is equal to dt. And then we just integrate from 0 to some time t, and I have no initial velocity, and I want to know my ending velocity. And notice that will be consistent with answer choice A. B has a sign error. C and D are just nonsense and separation issues. I do call this 3-star, though. All right, then to conclude, hopefully an easy question. Which of the following graphs correspond to a linear displacement of 20 meters? So we have position in A. I go from 5 to 20. So if I go from 5 to 20, and that's just an x, this would be plus 15 meters. If I go from 15 to 0, that's minus 15 meters. So it's not A or B. Then I have a V graph. So if I have a V graph, I want to find the area to find displacement. So this area is going to be, well, 5 times 4 is 20 meters. I know it's not going to be C because it's 20 meters plus whatever this triangle is, but just for completeness, we'll do it. We get 1/2 of 4 times 10, which I think is another 20. Does that make sense? It should. 1/2 times 4 is 2, and then my height is 10, yeah. And then by elimination, this triangle better have area 20, which it does, right? 1/2 times 4 times 10 is 20 meters. So hopefully we end with a little win here at the end of the day. All right. Yeah, I'd say this is medium hard overall. This question is supposed to be easy, but I would say overall these multiple choice are medium/hard on average, although there are some easy ones in there. Regardless, I think this is still a good review resource. Even if it might not be the most reflective of difficulty, you can definitely expect the real thing to be easier than this, significantly easier than this. The content is good, and that's what I find most important, is that we're reviewing the content. All right, free response next.